Greetings. I'm Doug Matson from Tufts University, and I'm here today to present a discussion of my vision of the trajectory of research activity over the next 10 years in space physical sciences. My expertise is in materials science, and I specialize in metal alloy solidification. As part of this work, I'm also extremely interested in the measurement of thermophysical properties of molten metals to allow me to develop models to control alloy phase transformations and microstructural development to improve the quality of ground-based manufacturing processes. Over my career, I've conducted experiments on the space shuttle, parabolic aircraft, and sounding rockets. And I currently run 2 experiments on board the ISS, one on solidification in collaboration with scientists from DLR and ESA using the ISS EML facility, and one on property measurement in collaboration with JAXA using their ELF facility. First, I'd like to talk about logistics, and then move on to the specific areas of research that my group would envision supporting over the next 10 years. Looking forward, we see the landscape changing significantly as NASA aims towards establishing a permanent colony on the moon with subsequent missions to Mars. There are many platforms that will need to be developed to reach this ambitious goal, providing a wide range of possible research opportunities in the physical and biological sciences. I will concentrate on 3 main arenas. First, I will talk about opportunities in low Earth orbit, or LEO. Next, I will discuss the opportunities for research as we transition from Earth to our target destination. And finally, I'll talk about activities at our colonization outposts, the Moon, Mars, and possibly asteroids. LEO is an old friend. We have significant expertise with the ISS, and it has served us well. Availability of power, cooling water, astronaut time, and telemetry are all key resources supporting our research. We need the station. But new facilities are on the horizon. Axiom has recently announced plans to use the ISS to incrementally construct a self-contained station to be released for use in space manufacturing and space tourism. For my science, this would require interlacing of tourist visits and manufacturing operations, since the G-jitter frequency generated by human activity is right at that critical value that's to be avoided when doing my science. Free flyers such as Blue Origin or Virgin Galactic provide fantastic opportunities for piggybacking science with resupply missions and offer the possibility for PI representatives to conduct microgravity research over longer durations than available using parabolic aircraft. Travel during staging operations is also an opportunity for research activities. However, given the constraints on cargo mass and volume, accommodations for science payload may be limited for physical or biological science investigations. Since Gateway is not to be permanently staffed, the lulls between visits are an attractive option for robotically controlled telescience, although opportunities for sample changeout will be a challenge to schedule. There are a host of important applied research activities that can be conducted on the lunar surface while taking advantage of commercial lunar landers and habitable outposts. A big question from a materials standpoint is, should we bring our living module with us or make them in place? Mars has a whole new set of questions relating to life support and basic maintenance and repair issues. In particular, do we know enough about conditions on the surface of the planet to evaluate material life predictions and risk mitigation? Moving on from logistics to research topics, the Science Mission Directorate has emphasized support for transformational science in 2 broad categories. First, the use of existing facilities, known as keystone capabilities, in new ways to advance both applied and fundamental research topics. Second, envisioning cross-disciplinary research campaigns involving multiple sets of investigators and a variety of research platforms to address a big picture issue in space exploration. On this slide, I've tried to capture my view of where I would fit in on use of keystone capabilities. The issue I would address personally would be manufacturing of metallic products in reduced gravity. There are fundamental studies that I would be looking at involving how convection influences microstructural development. The bridge between the fundamental and applied would be evaluation of thermophysical properties. This is work that must continue for us to understand about how measurement accuracy and prediction are influenced by the selection of what type of measurement technique we use, both here on ground and in space. And what we learn from our space investigations then allows us to have better confidence in our predictive capabilities here on Earth. The big hope here is to come up with some constitutive modeling and performance prediction, such that we don't have to bring all materials to space to investigate, but we would investigate a family of materials, learn how we can predict how small changes in composition would influence the properties, such that we only have to anchor the predictions through judicious choice of key constituents. And we'd be doing prototype demonstrations. So for instance, Made in Space is a very successful program. I would initially shoot for evaluation of additive manufacturing operations in a mid-deck locker and one of the free flyers, possibly leading to a prototype demonstration with initial investigations on parabolic aircraft. So technology demonstrations are going to be a key component of what I see as my research contribution, using existing facilities and moving forward to new transformational investigations. One of the big parts of the Science Mission Directorate activities is to investigate how we can look at these big picture issues, the grand challenge research campaigns. I've selected a few here. I would like to note that for my science, my research group, I'd really be most interested in supporting applied technology development. One issue could be maintenance and repair. When you're on your way to Mars, you don't want to bring a bunch of spare parts. If you need a tool, make it. We would emphasize recycling activities during the fabrication of these parts. And again, additive manufacturing would be a key component of this, but it's not the only issue. When we're no longer in zero G and we're now on the surface of some extra terrestrial body, we will have welding to do, brazing to do. So we are going to have operations that are going to be influenced by the change in the basic gravity conditions that we are in. And it's important to understand those. And life cycle analyses. How does the environment influence when we go and select a certain operational procedure? Does that have any effect on the life of the part? Second potential area for a grand campaign that I would be interested in would be in situ resource utilization. We have to put together habitable environments for humans for relatively short durations, but we'd like to be able to come back and reuse what we put up there. So do we have the capability to use the regolith as a concrete? Can we build structures there from the material that is there? Secondly, well, you can't bring an I-beam to Mars. So we'd have to be able to make large scale, long structural members in place wherever we decide we're going to be building a habitation. So again, how do you design an on-site foundry that allows us to actually make parts for use in severe environments? Water cycle is a key. Lots of things. It involves biologists, it involves fluid dynamics, and it also involves materials. How do you make the tubing and the fittings in place? Because you just can't bring a giant spool of tubing that you need. And what if it starts to leak? You need to replace that. There's going to be biofilms that develop in these systems. We would need to find out how can we coat the inside of operational surfaces in order to minimize the problems with that. How do you reduce fouling in a system that's operating for a while and then sits dormant for many months until you can come back and are required to reuse it again? Next, thermal management issues, heating, cooling, power. Dust mitigation. How do you keep the seals from degrading over multiple usage? And interestingly enough, what about mining? If we're going to do any long-term habitation, we need to take a look at how we can develop new materials to allow us to efficiently utilize the resources that are there. So I hope that you have enjoyed my discussion of some of the issues that I think are important, and I look forward to meeting everyone at our upcoming town halls. Thank you for your attention.